Alright, so today we're going to talk about one of the most important tools in AP Physics 1, which is drawing free body diagrams, or FBDs. So these diagrams essentially let us see all the forces acting on an object and make problem solving much easier. On the AP exam, correctly drawing an FBD often gets you partial credit, even if your math isn't completely perfect. So let's break down exactly how to draw them properly. So the first step would be to pick your object. Usually it will be either a circle or a box. And in your diagram, you'll pick one of these to start off with. And then you'll also make a coordinate grid with the object at the intersection of the two axes. So we draw the y-axis and the x-axis. You also want to make sure you scale the axes accordingly so that the forces make sense. So you don't want the thrust smaller than the friction if, for example, a car is moving in the same direction as thrust. Additionally, you also want the axis to be at the same angle that the object is moving in. So, for example, if our box is moving horizontally, then our x-axis should also be horizontal. It's not on an incline, so it will have a flat x-axis. Your second step is to label all of your vectors correctly for the correct force in the correct direction. You want to ensure the forces are also of the right magnitude and to scale. So, for example, this right here would be our normal force, since normal force is always perpendicular to the object. We can make this friction. This can be our applied force, and then the thing pulling the object down would be gravity. For this example, since there were no numbers provided, you don't have to assign them a value yet, but if you have a value, you should also ensure that you put them on the correct axis. Alright, let's try a practice problem. So here it says to draw a free body diagram of a box being pulled to the right across a rough floor. So we'll start by drawing our box. So since there are no numbers being provided, we don't have to worry about that. But the first force that we should always look for is gravity. So gravity is going to be acting straight down in this scenario. So we'll draw an arrow pointing straight down and label that Fg, which is force of gravity. And next, the second thing we should look for is normal force. So normal force will be acting perpendicular to the object. So instead of going this way, it will be going up. And we'll label that Fn, which is normal force. And since the box is being pulled to the right, that means that force is being exerted this way. So this will be our applied force. Next, since it's being dragged across a rough floor, we should also take into account friction. So friction will be pulling the object in the opposite direction that the applied force is going, so we have to draw the arrow in the opposite direction. And we'll label that FF, or force of friction. I want you to notice how the normal force and the force of gravity both cancel out in terms of their length. They're both equal. However, the horizontal forces, the applied force and the friction, don't cancel out because the applied force is longer than the friction. This is because the applied force is greater than the friction force, and so it's important to take into account the differences because you don't want all of your vectors to cancel out. Alright, let's try another problem. So in this problem, it says to draw a free body diagram of a 5 kilogram box that rests on a frictionless incline that makes a 30-degree angle with the horizontal. A rope pulls the box up the incline with a tension of 20 newtons. So let's first identify all of the different forces. So ask yourself what forces are acting on the box. First, we have gravity, and we also have normal force, and we have tension. Since it's frictionless, there's no friction here. Alright, now let's draw our incline. So this will be 30 degrees, and our object is being pulled up the incline. So we'll have our box right here. Let's think back to our forces that we identified. So first is gravity. So gravity always will point straight down, so let's point our arrow straight down. And this will be force of gravity. Let's do normal force. arrow will be perpendicular to the incline. So it's not just going to be straight up, it'll be perpendicular. So it should make a 90-degree angle with the incline. And we'll label that Fn. Now we do tension. So we have to draw the arrow up the incline since the rope is pulling the box upwards at a force of 20 newtons. We'll label that F of t. The tricky part with this is that gravity isn't aligned with the incline. So, like I mentioned earlier, we have to make sure that the force of gravity and the normal force cancel out. So to resolve the fact that these two forces do not cancel out, we should break the force of gravity into two components. So the first one will be parallel to the incline. So it would be this one. And then the next one would be perpendicular to the incline. Now that we have these labeled, we can start solving. So we'll call this the perpendicular one. And then this one will be the parallel one. So to solve for what's parallel, we'll set it up as mg sine theta. So mg would be 49, and then sine theta would just be sine 30. So all of that, once you put it into the calculator, would be equal to 24.5 newtons. Now to solve for the perpendicular one, we should do mg cosine theta, which is 49 cosine 30, or 42.4 newtons. So now that we see that the tension is 20 newtons this way, we also see that this one, the force of gravity parallel to the incline is 24.5 newtons. That means that we should edit our force of tension to be smaller than the gravity parallel to the incline. So instead, it would look more like this. We should also make sure that our perpendicular force of gravity cancels out with our normal force, which we can see that it does, so that's good. Alright, so notice how we first drew the main forces and then decomposed gravity into two separate vectors, and then finally compared the magnitudes to make it more accurate. It's always important to draw clearly, label your forces, and check if they balance or not. That way you can correctly and accurately start applying Newton's second law for the rest of the calculations. Thank you, and I really hope this helped.